So whenever resistors are connected together, there are only two ways really in which they can be connected. Okay. The first one is called what? In series. It's actually that's what it's called. In dash series. Go ahead. In series. Okay. The first one is in series, and the second one is in parallel. In parallel. Okay. By the way, this is what circuits is. Understanding how resistors are actually combined is really the make it or break it step in understanding circuits. Okay. And you'll see how on Monday and today as well. So, oops. The only other possibility is to what? Is to mix what? Is to mix these two arrangements. What does that mean? You can make an in parallel arrangement. You can make an in parallel arrangement with what in it? Or you can have an in series arrangement with what in it? In parallel. But you can always what? Always look and break every single part down to either in series or in parallel. Yes. No, resistors. I mean these ones. Remember the ones with the color code. These ones. Everyone. These are resistors. So how can you connect them in between like those two edges? You can connect them in series or in parallel. By the way, does anyone not have this? Not have it? Do you have it? Okay. All right, we're good? Okay. So let's talk about the first one. In series. How does any in series chunk look like? Any in series one looks like that. Go ahead, sketch that. Now, obviously, everyone, there are so many ways to what? To indicate resistors in a circuit diagram. The most common way is what? Is the what? Is the zigzag line. Can you guess why they actually chose this as the symbol for resistor in a circuit? I usually don't use this. I use a black box just because it's easier for me on Microsoft Paint to make a black box than this zigzag line. Question for you: if you're walking, if you're biking, and you run across this, is this a good chunk of the road or a bad one? Thank you. Exactly. So that includes introduces so much what? Friction. And friction in forces is what? Is what? Friction in forces is what in electricity? Resistance. That's why. So they always do this in resistance. Okay. Now think about it this way. Why do you think it's called in series? Is there any branching to this wire? No. Which means what? All the electrons that go through here, they still have to go through what? Here, here, and here. When there is no branching, we call it what? In series. It's like a perfect single chain. Perfect single chain. R1, R2, R3. I am choosing the current to go that way. I could have chosen the current to go the other way. Just a random assignment of the direction of the current. Okay? R1, R2, R3. Basically, if the current does not split, the resistors form a chain. That's what in series is. That's what in series is. Okay? So the question now is, by the way, the question always about circuits is, if I have a bunch of resistors, and I know all of them, how can I replace them with just how many? How can I replace a bunch of resistors connected in some way with just what? One single resistance or one single resistor. Why would that be needed? Well, sometimes maybe you're trying to make a circuit, but you don't have enough space to what? To put three resistors together. So you're like, okay, I better shop for one that exactly is what? Is the same or as powerful as all three what? As all three together at once. Okay? So that's basically what the first one is for. So let's go. Okay, everyone. So the equation that tells you the equivalent resistance. By the way, get used to this phrase: equivalent resistance, or REQ. Even in physics textbooks, this is how they use it: REQ. The mathematical equation for the equivalent resistance of any in series or chain part of the circuit is just what? R1 plus R2 plus R3. You keep adding until you get to the what? You keep adding until you get to the what? The last one in that particular chain. You don't just add all of them. You add only the one until the chain what? Until the chain what? Splits or forks or breaks, okay? But as long as you have a single chain, you can go and add as much as you want until you hit the last one in that particular chain. Exactly. So if you start and you know that you got up to 5 before you start branching off, you go R1, R2, R3, R4, R5, and all of these could be what? Could be replaced with what? One resistor that has a value of the sum of all of these resistances. Yes, exactly. Okay. All right. So let's do a simple example, I guess. Okay. All right. What is the equivalent resistance for a 25.2 resistor connected in series with a what? With another one, 28.12. I just told you it's in series and there's only two of them. What do you just do? You just add them up. Okay. So go ahead. So you just add them up. And yes. So REQ, you have to say REQ. Some people like to use R total, R overall. REQ seems to be the what? REQ seems to be the most common. REQ equals 25.2 plus what? Plus 28.12 equals, well, 25 and 28 is 53, and 2 and 12 is 20, and 12 is 32 in ohms. But according to the sig fig situation, what do we have? How many sig figs here? Here 4, and here's 3, so we have to go down to 3, which is 53. Okay, that's it. All right. Okay, easy enough. Okay, I think we have another demo. How about 53 connected in series like this? Yep. So R1, R2, R3. But guess what? R1 is equal to R2 is equal to R3. So when you add three things that are identical, you just end up multiplying the whole thing. So REQ in this case, only in this case, because they're all identical, 3 times 53.0, which is how much? 159. Okay. It is. It is, you're right. But when we put it in a big circuit, then it actually what it becomes just the elaborate part of the mechanical process. But as far as we're concerned here, not too bad. All right, let's go with the next one. The one that's definitely a bit more interesting and uh, harder to compute. Okay. All right, parallel. What's the difference between this one and the first diagram? The first diagram had a single what? Had a single line or chain. How about now? You have a what? You have a ladder, you have a stack, you have way too many ways to what to call it. I like to call it a stack. So basically now, what's happening to the current if it goes here? What's going to happen to it? It's going to split, exactly. So whenever current splits into 2 or 3 or 100, that is called what? This right here is called an in parallel arrangement because they're what? Kind of like parallel to each other as the rungs of a ladder. Okay? So basically, R1, R2, R3, and it's going in, it branches off, goes through each one, goes again, combines, and comes out. Now, here's my question to you. Is it always going to be that the same amount of current goes through each part, each branch? What do you think? So my question is the same amount of current or electrons or the same density of electrons going to go through the R1 resistor as much as the R2, as much as the R3? Could it happen like that? Is there a possibility that the split will be a perfect triple split? So as much here, as much here, as much here. Think about it this way. If I have 3 amperes going here, 3 amps going here and split, is there a possible way that 1 amp goes here, 1 amp goes here, and 1 amp goes here? But that's only possible in one and only one single possible condition, is for all three resistors to be the what? To be the exact same, right? What if this resistor is much, 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 much bigger than this one and than this one as well? What? Sorry, say again? You mean in every case, or what are we talking about? So if resistor 1 is the biggest one, what does the resistance mean? Are you allowing a lot or a little? So if your resistance is super, 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 super high, are you allowing super much or super little? So, thank you. What do you want to say? Thank you. Where do you think the word, the phrase, the path of least resistance comes from? From here, right from here. If you have a lot of resistance, what does that mean? Are you going to allow a lot or a little? which means if this one is 1,000 ohms and this one is 1 ohm and this one is 1 ohm, you know two things. You know this one is barely going to pass any, and most of them are going to pass through what? These two. Also, because these two happen to be the same, they will what? They will pass unequal or equal amounts of current. Equal amounts of. But Ali said it best. The phrase of path of least resistance comes from this part of electricity. You always go through the what? The least amount of resistors possible. Okay? I have a question for you. What if you listen up, everyone? What if you cut this? What if you cut the wire? What's gonna happen? Let's say, okay, you're right. You have a point. Which one? Randomly, I cut the top one. How is that gonna affect the flow of electrons in the circuit in the new one now? Question for you. If you cut a wire, can electrons go through that wire? Why not? Because they can't what? Exactly. There's no path unless, by the way, unless in one case, unless the voltage, like of the battery or the current in that wire is so big, it could actually ionize the air like lightning. Then what happens? Because it's so powerful, it's gonna ionize the air in between the like the severed part of the wire, and that ionized air will be what? Will be a conductive path. Do you see what I mean? But thank you. Do you think it's easy to ionize air? Absolutely not. Air needs to what? A huge amount of what? Of energy to be ionized, which means unless you provide it with what? With a huge battery, you're not gonna be able to ionize air. So we assume what? We assume when you cut, is there any current going through? So it's interesting. When there is zero current going through, what's your resistance? No, hold on. When there is zero current going through, when there is nothing going through, it's as if your resistance is what? Infinity. Thank you. Does it make sense? If you have infinite resistance, you pass what? You pass no current, which means what then? All the current has to redirect into what? Into the other two. Could that be dangerous? Yes, because what if those two wires are not designed to what? To take. Thank you. To take the what? To take the rest of the what? What? And that's exactly how your what? How a power surge works. A power surge detects that basically what? This wire or this section of the circuit cannot take this load. So what does it do? The circuit breaker. That's why it's called a circuit what? Circuit breaker. It breaks the circuit and it just makes what? Make sure that it doesn't go through the rest of it to fry the circuit. Is it making sense? That's basically it. So someone says it's always to connect things in parallel. Is it always good? Is it always good to connect things in parallel? It's good and bad. It's good because what? What's the only good thing about connecting things in parallel? By the way, the things in your house, the appliances in your house, are they connected in series or in parallel? Okay, question for you. What would happen to a house where all the appliances are connected in series? If you sever it once, the whole what? The whole line is gone, right? But if you do it in parallel, what does that mean? If one appliance if one appliance fries, you still can what? You still can direct it. But the problem is what now? You have to design the other wires such that what? On average, they can what? Handle a what? Handle a bigger load. Is it making sense? So parallel is always a better design, provided you what? You designed it with a backup contingency plan to what? To take the extra load. Perfect. Awesome. Okay. So if they do split, sorry, if the current does split, it forms a stack. Stack means what? The stacked up parallel layers. Okay, so the question now is, what's the equation for what? What's the equation for a bunch of purely connected in parallel resistors? Okay, how easy was the equation for the series? What did you just do? You added them up. Ladies and gentlemen, here's the equation for the in parallel. Hmm. The equation is 1 over Req equals. So is it kind of similar to the first one? So instead of adding them, you will first what? You reciprocate first and then you add. What do you think is the most strong way of writing this equation? Which, by the way, sadly happens to be a common mistake. Think. How could people, by the way, that's why I never ask people to memorize. How could people memorize this the wrong way? Yes. No. Sure. No. That's legit. But there's another even worse way. Instead of what? flipping and then adding, what do? They add and then flip. The most wrong way is many people do this. 1 over REQ, and they just do this. 1 over what? R1 plus R2 plus da 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 plus R last. Is that equation the same as that equation? 100% no. I mean, think about it. You know what? Forget that you have so many of them. Even if you go down to what? Even if you go down to 2. Everyone, imagine if this was a 2 and this was a 2. Okay? What's 1/2 plus 1/2? Good. What if you did the 2 plus 2 here? What would you think you would end up with? 1 over 4. Completely the wrong addition. So please don't add and then flip. No, flip each one and then add them. But guess what? Even if you do that, you're not yet fully done. Because is that equation solving for REQ or 1 over REQ? Which means once you're done with that fraction, what do you have to do with both sides? You have to reciprocate or you have to flip. Thank you. Exactly. Okay, so this would be the wrong way. There you go. Go ahead. Remember, you have to flip or reciprocate the result of the above calculation to actually get the actual final value of REQ. Okay? Yes. Okay. Polymerization. Polymerization is just making what? Making a polymer, or basically we're connecting so many carbon atoms together to make a long chain hydrocarbon. It's not. It's just polymers usually are insulators. That's what we bring them up. No, they are very, very, very weak connectors, which is amazing because they insulate. So that's why when you work with electricity, you always wear what? Rubber gloves. Yeah, because carbon by default, especially when it polymerizes, like forms long chains, it becomes a very what? A very weak electrical conductor, which makes it a very good electrical insulator. Yes. Okay, okay, everyone, demo, come on. If you connected a 120 to a 60 in parallel, what is the resultant one single resistor you can replace both with? Okay, so let's catch a quick diagram, everyone. So this is it. Here's one stack. Sorry, here's one part of the stack, and here's another one. Okay, it doesn't matter which one is on the top. So 120 ohms here and 60 ohms here. Okay, what do? 1 over REQ equals 1 over, I'll guess I go with 120 plus 1 over 160. Now, obviously, you can just plug this in into your machine and call it a day. But come on, how would you add these two fractions? You will need a common. Yes, thank you. Oftentimes, it's not that bad. What's a common denominator between 60 and 120? The 120 itself. So one fraction doesn't need to be changed. So 60 times 2, 60 times 1 times 2. All right. What does this mean? 1 over REQ equals 120. 1 over 120, my bad. Plus what? 2 over 120 plus you. Makes it what? 3 over. Now you have a choice, everyone. Can you simplify this fraction? Can you simplify 3 over 120? Yeah, because it's like 3 over 12. So you can simplify and then what? Flip. Can you flip and then simplify? Yeah. Either way, you're gonna have to do both of them. So let's simplify. So 1 over REQ. Hold on. Why what? Why do I need to flip? No. Oh no. By that I mean I need to bring the REQ on top. Because remember, it's like you didn't solve for the x yet. You just got the 1 over x step. Do you see what I mean? You're not fully out of the woods yet. So you look, this means if you flip this fraction, then fairly you have to flip this fraction as well. Make sense? By the way, what's another way to do this? Cross multiply. But why would you cross multiply when you have a what? When you have a 1. If you flip this one, the only possible logical choice is to flip this one as well. Exactly. There's no need to cross multiply. And if you cross multiply, you would end up with the same thing you'd get if you flip. So 1 over REQ is 1 over 40. Hey, no need even for a flip. If 1 corresponds to 1, then REQ corresponds with what? With 40. So that means REQ is 40 ohms. Okay. Get up to here and pencils down. Okay. Question for you. Listen up, guys. Go to the first two demos of the series. What was the first two demo of the series? What did we connect with what? Come on. Ah, the first, yeah. We connected what to what? The first demo problem in the series. Yeah, but what were the values? Sorry, what were the values? We connected a 25 to a 20 what? To a 28. And what was our answer? 53. So our answer was what? Smaller, equal to them, or bigger? It was bigger than the biggest one. What was the biggest individual one? 28. Okay. How about the next one? No. How about the next one? Next in series. You connected what and what and what? You connected a 59 to a 50, sorry, 53 to a 53 to a 53. The equivalent resistance was what? 159, which is bigger than the biggest of them, and they happen to be the same anyway. How about here? It's not just smaller. It's smaller than the what? Than the smallest. And that's how what? That's how in parallel always works. When you do in series, your answer is always what? Bigger than the what? Bigger than the biggest that goes into the mix. In parallel, it's what? It's lower than the what? Than the lowest one that goes what? Into the what? Come on, into the what? Into the stack or into the mix. Is it making sense? So what does that mean? If I give you, everyone, if I give you, where's the, one second. Ah, everyone, if I give you, how many resistors is that? 1, 2, 3, 4, 5. And I ask you, guys, and I ask you to connect them to produce the biggest resistance ever. How are you going to connect them? To produce the biggest thing you can ever produce. Then you have to produce what? To connect them this way, right? You have to connect them like this. Make sense? It goes in between, right? How about if I wanted to use them to produce something lower than the lowest one by reading the color code? How do I put them? I have to put them in what? In. Is it making sense? So whenever engineers wants to what? Lower the resistance, they what? They tweak the arrangement to make it what? More in what? More in parallel. If they want to increase the resistance, they tweak it to more, can make it more in what? More in series. There you go. You got it. Okay. Okay. Another demo. What's the equivalent resistance of 420s, identical, connected in parallel? All right. Now I have a what? I have the following stack. Let me fix the top one. No, not good. You have to connect it that way. They have to all branch exactly from the same point. Yes. See? Yeah, they branch this way, this way, this way, this way, this way. Did you do make a perfect stack like I did? Yes. Everyone, technically, this makes sense, but it's better and more symmetrical to always get used to doing it this way. Yeah, kind of like maybe a tree diagram in a way. I guess if you imagine a tree diagram with branches. Yeah, what's up? You're not in my course, but I would really, really urge you to always sketch it like that, please. Yes. Oh no. Yeah, thank you, Yasmin. I just randomly chose the current to be coming from this side of the diagram. That's all. Okay, all of them are what resistance? All of them. 20. So 20, 20, 20, 20. Okay, let's do my REQ. 1 over REQ. Is this correct? Is this correct? Is this correct? The equation. No. What was the mistake? Aha, I have to what? I gotta flip first and then add. The problem here, I added and then flipped. That is wrong. So it has to be properly. I know. I'm not cool. That's fine. 1 over REQ is equal to 1 over 20 plus 1 over 20 plus 1 over 20 plus 1 over 20. Come on. No need for machines here. What's 1 plus 1 plus 1 plus 1? 4 over, what's 20 plus 20 plus 20 plus 20? You don't do that. Yes. Say again? No. Okay, everyone. Yasmin is saying, listen up, guys. You're saying that the first one was correct? But the problem is if I did the first one, it will be 1 over 80. No, I'm not. Even if okay, everyone, can someone tell me, how does this one simplify? What's 4 over 20? Divide both by 4, you get 1 over 5. You see? But but this is the proper way. Also, what's another proper way? What's something added a bunch of times? You could have just multiplied 4 times 1 over 20. Yeah, 100%. Again, as long as all of them are the what? Are the same. Yeah, of course. Again, as long as you know the physics, math offers you multiple ways. So this is what? 1 over 5. What does that mean? Oops. What's the logical check that my answer makes sense? What's my final answer? 5. And it's what? Lower than the lowest. Well, they're all 20. Perfect. Done. That's it. Okay. We're good? All right. 3 resistors are connected in what? I am telling you, they form a perfect what? A perfect what? Straight chain, straight string. Okay. 2 resistors are the what? Have the same resistance. They're as powerful as each one. While the third one is what? Twice the resistor of each. Okay. By the way, am I telling you which one is first, which one is second, which one is last? Do you think it really matters? No, because eventually what you're going to do to all of them, add them up, so it doesn't matter, okay? But I'm a big fan of symmetry, so when we sketch them, I like to put the what? The 2 identical ones on the peripheries and the big one in the middle. Okay. The voltage across, everyone, listen up. The voltage when you connect the hooks from the very far right of the whole string to the very far left reads how much? Reads how much? 27 volts, like 3 9-volt batteries. Also, I'm telling you already that the entire thing is how strong? Come on. 3.6 what? What's a small k? Kilo ohms. Okay. Question 1. Sketch a representative diagram. What do you think I should sketch? How many resistors do I have? 3. And they're connected perfectly in what? In parallel. Sorry, in series. So go ahead. Let's sketch it this way. Just follow my lead here. Okay, come on. Obviously, I'm going to sketch. We don't need really all of this space, but let's say we do. Here is the string. Okay, here's my first one. Here's my second one. And here's my third one. Okay, let's put some numbers. Do I know what the 3 of them are? I don't, but I do know that 2 of them are identical and one of them is twice as big. So if I call everyone, look, if I call this one R, if I call this one R, and I call this one also what? Then definitely the middle one has to be what? 2 times R or 2R. You got it? Good. Okay. What else could I put on this diagram? Oh, I could put, by the way, I could put randomly that I assign the direction to go this way. It's complete. Yes, the voltage is how much? 27. But you have to connect the hook here, everyone, here and here. So go ahead, connect, make the wires come out, and make like a dial screen. And 27 volts. Good, good. Okay, what's the last number? Come on. What's the last piece of information? All of them combined are how much? 3.6 kilo ohms. So I can put this where? Maybe here. Everyone, you can just put R EQ is equal to 3.6 kilo ohms. Okay, obviously, when you do your calculations, you're gonna have to switch from kilo to just what? Single legit basic ohms. Yeah, you could. But yeah, feel free to make it what? What would this be in single ohms? 3,600 or 3,600. Yes. Okay. Question one. What's the current through this section of the circuit? What's the symbol of the of current? Symbol, not unit, symbol. I. How many equations did I teach you with I in them? Two. What was the first one? I equals what? Q over delta time. Are you given any charge information here? Are you given any time information? So that's completely useless. What's the other equation with I in it? Ohm's law, which is what? V equals IR. Okay. Are we given voltage information about the whole section? Uh-huh. Are we given the resistance of the whole section? Got it. So we can say what? I, uh, just I equals what? V. I know, but I want you to write subscript. V overall over R of section. R of the whole section. Okay, what's um okay, Yasmin's asking, it doesn't matter. Not here, but because I'm gonna give you what eventually very big circuits, you're always gonna be what call it exactly. Talk about one part. So that's why you should always what talk about either the part one, part two, part three, part four, or the whole section. Okay. So what's the overall voltage? 20, 27. Baha, what's the R of the whole section? 3,600. What is this divided by that? Point? No. 27 out of 36 is 0. Okay. In this unit, sorry, in this scale, what unit is it? Just what? Is this in milliamps or just in amps now? Now, right now it's in amps. Okay, what is this in scientific notation? 7.5 times what? 10 to the. Hey, what's the scale of -3 already? What's milli? It's already done for us, which is interesting because that's what the question is asking for. Great. So this is what? 7.5 milliamps. This part just becomes M. Done. Yes. So we divide. Hold on. We divided, right? And in scientific notation, 27 divided by 3,600 is 7.5 times 10 to the -3 amps. Oh, Baha, why is it? Yasmin's asking, why is it 3,600? Because it's using kilo ohms in the question. I cannot have what? Sorry, I cannot have kilo in the scale. So I have to what? Multiply it by 1,000, giving me what? 3,600. Okay. By the way, most of the time when we use these resistors are in the scale of what? In the scale of no more kilo ohms, mega ohms. By the way, an ohm is a very small amount of resistance. Very, very small. That's why we usually go to what? Kilo, mega, and so on. Okay? Yasmin, we're good? So 10 to -3 just by dividing these two. Okay? Oh, sig figs, my bad. What's the sig fig situation, everyone? Is it 2 or 3? Oh, my bad. Then I should add 0. Sorry. Thank you. And this should be 0 as well. Oh, yeah. As a standard notation. But to play with the scale, I had to put it in scientific notation. That's all. I did this, but most of you probably did not get this. Most of you probably got this one. That's all. Okay. Ali, what's the second question? What's the what? What's the resistance of each resistor? Okay. How many resistors do I have, everyone? Come on. 3. And they're all connected in what? And I happen to know the addition of all of them. So can I find out what each one is? Yeah. You know why? Because I did not call them what? Look, I did not call them R1, R2, R3. I called them what? R, 2R. Yeah, I did not call them 3 different unknowns. I related them all to how many unknowns? 1, which is basically either the magnitude of this one or the magnitude of this one. But you know what? Everyone, I want you to write R1 here, R2 here, R3 here. we already know that R1 is going to be R, R3 is going to be R, and R2 is going to be 2R. Okay. Now, they're connected in series. What's the law for series? Do you flip or do you just add? You just add. So Req equals R1 plus R2 plus R3. However, this Req has been known to be 3600. And this R1 is R. And this R2 is 2R. And this R3 is R. Yes, exactly. Yep. Remember a math teacher when they say the let statement? Do you know the let statement? Yeah, exactly. Let R be the resistance of one of the small ones. And then you relate everything to it. So 3600 is equal to what? 4 R's. This translates to what? R equals how much? 3600 divided by 4. How much is that? 900. Now 900 what? Yeah, but I need my answers in what for some reason? Kilo ohms. How do you go from ohm to kilo ohm? You divide by 1,000. So technically, your R's are the following. R1 is the same as R2. No, sorry, R1 is R3. R1 is the same as R3, the way we place them, are equal to 0.900 kilo ohm. Because you divide 900 by 1,000, you don't get a full one, you get less. However, how about R2? It's equal to what? 2 times that, because it's twice as big. How much is double the 0.9? Come on. Double the 0.9? Yep. Nice. Not bad. Makes sense. Are we making sense so far? I'm trying to relate circuits to the basics of what of V equals IR and even before. Yes, yes, me. No. Okay. Everyone, why can't I divide by 3? Because sadly, they're not all equal. Remember, you can only divide it by 3 if they're all what? Triple identical twins. Sadly, one of them is twice as big. Is it making sense? So instead of multiplying, I'm just going to add them up. Okay. Last question. Is it last question or is there one before? After? Sorry. If the current took zero point 0.7 seconds, whoa, what did I just give you? 0.7 seconds. That's a value of what? Time. Okay. 0.7 seconds to go through. How many electrons is that equal to? Okay. What's the only equation, everyone, that has the number of electrons in it? No, no, no. I want the equation with the number of electrons in it. With the number of electrons in it. Q equals Ne. But the problem is, I don't have the Q yet. Okay. Do I have another equation that relates Q to this stuff? Yes, I, exactly. So this is a two-step calculation. The first step, everyone, is I equals Q over delta T, which means what? Crisscross, you get Q equals what? Actually, let's do it here. My bad. Everyone, let's do it here. I delta T. Remind me again what was my current that we found? Or 7.5 times 10 to the negative 3, yes? So 7.5 times 10 to the negative 3. And what's my time in seconds? Great, 0.7. Go ahead. What's this answer? By the way, what's the unit for this answer, even before knowing the number? What's the unit? It's a charge. It's a charge. It's in what? It's in legit coulombs. Sorry, what did you say, Ali? I just amps. Well, amps is the 7.5. Dementia already? All right. What do 7.5 exponent of 3 negative times what? Times 0.7. How much? 0.0525. What's this in scientific notation? Remove it 3, 5.25. Yep, 5.25 times 10 negative 3. I mean, you could have written as standard. I don't really care. So 5.25 times 10 to the negative 3. Okay, and now, Mariam, what am I going to do with this number? Apply it to which equation? The equation for the number of electrons. Q equals Ne, or N equals Q over E. Done. N equal Q over E, which is 5.25. In the book, maybe not, but it's in the notes. Which equation? Which equation? This one or this one? I'm not sure. I want to say it's there. Well, it's in the notes. That's what you're saying. You found it in the textbook? Oh, apparently it is. I think I saw it once. What's the magic number? 0.6. Okay, I know the concept, the power of 10 by heart. It's the 316. 5.25 divided by 1.6. That is 3 point. Technically, the sig figs now have to sadly go down to 2. So 3 point what? Just one more. 3.3. Is this in C or in E's? Because it's a huge number and it's the number of electrons going through. Thank you. Can someone play with this for me? Remember, I want you to play with the 10 to the 16 using the scales. Come on. What scales do we always deal with? 3, 6, 9. 3 is 1,000. 6 is a million. 9 is a billion. 12 is a trillion. We don't. Okay. I mean, you could go to 15, but let's say you could not go more than 12. So apparently, you are gonna steal 12 from here. How many remain? 4. So that means what? Everyone, look. If you want, 3.3 times 10 to the 4 times 10 to the what? 12, still in ease. What's so this one is what? Trillion. And what's 3.3 times 10 to the 4? 33,000. 33,000 trillion electrons pass through the circuit in as little time as 0.7 of a second. Yeah, they're fast and they are very small. Good. Last one. What's the amount of work done? Oh, okay. Now, you see how many equations, including work, you have now? I don't. Okay, what's the equation for power? Delta T. Yeah, I don't. But yeah, everyone, listen. Everyone, good question. Listen. Yasmin is saying, can you use this? P equals W done over delta T. I mean, I have it, but I don't have my power information. Did I tell you what's the power of this circuit? I didn't tell you. All right, so this is completely useless. Can you use work equals force times distance times cosine theta? Not here. Can you use work equals E final minus E initial? Also not here. Okay, come on. There is one equation with work that we learned in this unit. Nope. Electric force doesn't have the work in it. It's K Q1 Q2 over D squared. Come on. What's the only equation with work that we covered in this unit? Just yesterday, in the first half of the day. Come on. Look through your notes, people. That's why you're struggling with tests, because you're not quick with your notes. You just keep waiting for me to say the answer. Come on. Come on. I need an equation with work. Aha. Yes. Voltage is what? Work done over charge moved. Done. That's it. So, yes. Delta V equals work done over Q. How do you crisscross? W equals what? Q times delta V. What's the Q? Come on, we already got the Q. How much? Yep, 5.25 times 10 to the negative 3. And what's the V? What's the voltage of the whole section? 27 volts. That's it. That's it. And since everything now started to become 2 sig figs, it's 0.14. 0.14 what? It's work, people. It's work. Joules. Yes. Work, work, work. I know, I unleashed the beast. You see how everything is still related? You just need to know where it is in the notes.